Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this module is about orthogonal frequency division multiplexing, or OFDM. OFDM is essentially a technique for dealing with a dispersive channel. Now, a dispersive channel is any channel where the receiver gets multiple received copies of the transmitted signal that all arrive at different delays and at different strengths. And this typically occurs when there are reflections or echoes in the channel. So a classic example is the wireless channel, where the receiver gets many reflected copies of the transmitted wireless signal that bounce off of objects in the environment. Another example is a wired channel where there is not a perfect power match between the impedance of the cable and the impedance of the receiver. So this often happens, for example, with digital subscriber line or DSL modems. When there's an impedance mismatch, there is energy reflected back from the receiver that bounces back and forth on the cable and results in multiple reflected copies of the received signal. And traditionally, equalizers have been used to deal with dispersive channels. Equalizers are essentially tap delay line filters that seek to invert the channel response of the dispersive channel. Now, equalizers have been used for many years and still are used, but the problem that people started to encounter with the equalizer as data rates increased was that as your data rate increases, your bits get skinnier, and the dispersion in the channel then causes more intersymbol interference over a larger number of bits. And this resulted in equalizers that needed a larger number of taps, which increased the computational complexity. So OFDM has emerged basically as a much less complex way to deal with intersymbol interference caused by dispersion. And it's been so successful that it's now, I think safe to say, it's used in the majority of digital communication systems, both wired and wireless, currently being used today. So the fundamental idea behind OFDM is it takes advantage of the fact that a dispersive linear time invariant channel, or LTI channel, can't cause intersymbol in a sinusoid. Or maybe more accurately, we would say that ISI, due to dispersion, doesn't change the fundamental shape of a sinusoid. So for comparison, let's say we've got a square pulse and we transmit it through a channel with a bunch of reflections. What we're going to get at the receiver is, something that starts out square but has a little bit of a tail to it due to the dispersion or the reflected copies that arrive at later time delays. And so that fundamentally changes the shape of the signal that we've transmitted. What we're going to see is that the same does not occur when we deal with a sinusoid. And so to illustrate this, let's look at an example. So let's consider a channel h of t that has two reflections in it. So a channel impulse response for a dispersive channel typically has one delta function for each reflection. This first delta function arrives at a delay tau 0. The second delta function arrives at a delay tau 1. And each delta function is multiplied by a complex weight, C0 and C1, that represent amplitude and phase distortion that occurs when the signal bounces off of whatever it bounces off of. So if we convolve our transmitted signal then is a sinusoid, a complex sinusoid with an oscillation frequency of Fc, which we would call the carrier frequency. Now, if we convolve our transmitted signal with our dispersive channel, we get two exponential terms. The first one multiplied by C0, second one multiplied by C1. We still have our frequency of oscillation Fc, and then we have an additional phase term due to the delay tau 0, and the second one due to the delay tau 1. That should be a 1, not a 0. And if we sort of simplify this a little bit, we find that our received signal is still an exponential, complex exponential with an oscillation frequency of Fc. However, it now has an additional phase term, and its amplitude V is equal to the magnitude of C0 plus C1, and this phase term is due to the phase of C0, the phase of C1, and also the phase shifts due to the delay tau 0 and tau 1. So what we see here is that dispersion will change the amplitude and phase of the sinusoid, but it doesn't change the frequency of oscillation, and it doesn't change the fundamental shape of the sinusoid itself. And we can also look at this robustness to dispersion in the frequency domain. So let's consider our transmitted signal S convolved with our dispersive channel H in the frequency domain, where we take the Fourier transform of the convolution. And of course, the Fourier transform of a convolution is just a multiplication of the frequency response of the two terms in the convolution. And so if we denote H as the Fourier transform of the channel response, the Fourier transform of our sinusoid is just a delta function. So typically when you have a dispersive channel, H is, we'll have a shape that looks like this. And that will typically, if the transmitted signal has a non-zero width, that will typically change the shape of the signal in the frequency domain, which changes the shape of the signal in the time domain. However, if our transmitted signal has zero width, as is the case with the delta function, it can't fundamentally change its shape. And that's what I'm trying to illustrate here. So if we have a transmitted signal, this should actually be S of F, that has some width, and we transmit it through a dispersive channel. A dispersive channel typically has these nulls. When we multiply S of F with H of F, our received signal Y of F is going to look something like this, which is a fundamentally different shape than what we started with, right? So we get distortion of our signal. However, if S is a zero width delta function, it will be multiplied with H of F, and it'll multiply basically whatever, portion of H of F that it happens to overlap with. However, because the transmitted signal is zero width, we get a received delta function. And again, we fundamentally do not change the shape of our transmitted signal. Now we've seen that the dispersive channel distorts the amplitude and phase of our transmitted sinusoid. Now, this is not distortion that we can just ignore, because of course most of our modulation schemes manipulate the amplitude and phase of the sinusoid in order to transmit information. And if we have amplitude and phase distortion, then our transmitted information is corrupted. So we do need to remove the amplitude and phase terms added by the dispersion. And so let's consider an example where we are using a sinusoid and we have an amplitude AM and a phase theta m, and both this amplitude and phase term carries information, right? So we want to preserve it at the receiver. However, our amplitude and phase is obscured in the dispersive channel by the magnitude term V and the phase distortion term phi. So we can remove this by using something called a one tap equalizer, because we can basically use it remove it by a single multiplication operation where, each tap in an equalizer requires a multiplication. So that's where the name comes from. So the first thing we need to do is estimate the amplitude and phase distortion caused by the channel, and we do that using something called the pilot signal. So we transmit a signal where S of t is basically equal to 1. Or if you like, this can be implemented with a sinusoid with a magnitude of 1 and a phase of 0. So we transmit this pilot signal at a known time. The receiver is expecting it, and then the receiver examines the magnitude and phase of the pilot signal that it receives, and it knows that any amplitude and phase change it sees in the pilot must have been caused by the channel. And so the received signal would then be equal to our dispersive magnitude and phase multiplied by our original pilot signal, which is just equal to 1. And so the way that we remove our amplitude and phase distortion is first I'll write the received signal as our desired magnitude, our desired phase, multiplied by our phase distortion, right? And that's just a simplification of this, or just another way to write the equation up here. And then our equalizer value, or our tap value, if you like, that removes the amplitude and phase term is just exponential with a minus phase, and then the inverse of the magnitude distortion v. And of course, this v cancels that one, and this negative phase cancels this one, and we recover our original transmitted information. And this will always work as long as we use a pilot signal to estimate the amplitude and phase distortion that the dispersion is causing. So at this point, we know that the sinusoid is, or dispersion causes magnitude and phase distortion for a sinusoid, and we now know this one tap equalizer technique that allows us to remove the distortion. The next step is to sort of start thinking about some kind of practical implementation issues. And the first one is that we have to remember that a continuous time sinusoid has an ideal delta spectrum only if it has infinite duration. Now, the reason why this is a problem is because we want to use this sinusoid to transmit information. And so we can't have the sinusoid, have a constant amplitude and phase for all time, because then that's not very interesting from an information carrying point of view. And so what we really want to do is we want to chop the sinusoid into little pieces and use each piece to have, or give each piece a different magnitude and phase according to our modulation scheme, in order to, transfer some sort of information at a certain data rate. The problem, though, is that when you truncate a sinusoid, like I've drawn here, basically truncating a sinusoid in the time domain is like multiplying it by a square windowing function. And when you take a sinusoid and you multiply it by a square window in the time domain, you convolve that delta function, you convolve the delta function frequency response of the sinusoid with the Fourier transform of the square pulse, which is a sinc function. So rather than getting a nice delta function in the frequency domain, now you get a delta function convolved with the sinc, which looks something like this. Now, the reason why this is a problem is because in order for the sinusoid to be robust against a dispersive channel in the frequency domain, it has to have zero width. And as soon as it has non-zero width, then when we multiply this sinc spectrum by the dispersive channel, which has these nulls, it's going to change the shape of our transmitted signal and result in distortion. And so the way that we get around this is by starting to think about our sinusoid in the discrete time domain. So rather than thinking of a continuous time sinusoid, let's consider a discrete time sinusoid, or a discrete time signal denoted x of n. The reason why this is an advantage for us is because when we want to look at our discrete time signal in the frequency domain, we use a discrete Fourier transform. And a discrete Fourier transform operates over a finite sample window rather than from -infinity to +infinity. The implication of this is that it's now possible to work with a truncated sinusoid and still have an ideal delta function in the frequency domain. And that's what I've tried to represent here. So over here, I've drawn a discrete time sinusoid where the stem plot represents the samples of the sinusoid. And when we take the discrete Fourier transform, we get ideal delta functions in the discrete frequency domain. And so this Fourier transform operation, again, is performed on only k samples. And so what this means is that we can now chop up our signal. If we're thinking of our signal now as a discrete time signal, we can chop it up, give each little piece a different amplitude and phase according to our modulation scheme. And as long as we use a discrete Fourier transform, we still have a nice delta function in the frequency domain. So we have this nice property of the discrete time signal as being, truncated and still robust to the dispersive channel only on one condition. So in order for the discrete time signal to have the same nice properties as the continuous time sinusoid, the dispersion has to affect each sample in our DFT window in exactly the same way. And so basically what we need to do is we need to extend our waveform beyond the start of our k-sample window. And so this section of the waveform, is our k-sample window that's being operated on by the DFT. Now, dispersion is going to cause a smearing where this sample sort of smears into the next one, this sample smears into the next one, this sample smears into the next one, right? And so all of these samples are smearing into their neighbors. And in order for, for example, the first sample to experience the same kind of dispersive distortion as this sample, then it has to have its neighbors smearing into it in exactly the same way as we have smearing over here. And so basically what we need to do is we need to extend our sinusoid in the left-hand direction so that the dispersive channel will, as I said, affect each sample in our k-sample DFT window exactly the same way. And so this gives rise to something that's known as the cyclic prefix. Again, the black samples represent the k-sample window being operated on by our DFT. And we want, and our dispersive channel has this much width, which basically corresponds to, in this diagram, let's say maybe 1, 2, 3, 4, 5, 6 samples, right? So the dispersive channel basically will smear 6 samples together. And what we do then, in order to make sure that the dispersion affects all of our samples equally, is we take a copy of our transmitted sinusoid from the end. We take a copy of the end of our transmitted sinusoid and attach it to the beginning of our transmitted signal. And as long as the width of this copy is greater than the width of our dispersive channel, then all of the samples in our k-sample DFT window will experience basically the same dispersion and will be robust to intersymbol interference in exactly the same way as a continuous time sinusoid. And these samples are known as the cyclic prefix. Cyclic because we take the samples from the end and wrap it around to the beginning, and prefix, of course, because it's put at the beginning and not at the end. Now, we're basically adding extra samples to our transmitted sinusoid, but it's important to note that the DFT only still operates on K samples. So basically at the receiver, we would discard the cyclic prefix. It's done its job, and then we would perform the DFT only on the K samples that are left over. Now, in theory, we are now at the stage where we have a working communication system that is robust to the dispersive channel. We've got our sinusoids that we can take a long sinusoid and chop it up into little pieces, change the amplitude and phase of the sinusoids according to our modulation scheme. And as long as we implement the cyclic prefix, once we sample our transmitted sinusoid at the receiver, we have every little sort of piece of the transmitted sinusoid will experience only amplitude and phase distortion, which we can then remove with the one tap equalizer. So we kind of have a communication system sort of put together now. The problem is, though, that the cyclic prefix represents overhead, right? Because it's discarded at the receiver. And because of that overhead, we have to sort of look for ways in order to increase our throughput. And so this is where we come to the multiplexing part of orthogonal frequency division multiplexing. So a K sample, so remember our receiver operates or does its DFT operation on K samples of the received signal. And a K sample window can contain up to K orthogonal sinusoids called subcarriers. And so to be orthogonal, sinusoids, if we're talking in terms of discrete or DFT frequency or discrete time frequency, sinusoids are orthogonal as long as their carrier frequencies are offset by 2 pi over k, where k is the number of samples in our being operated on by our DFT. And the nice property of orthogonal sinusoids is that orthogonal sinusoids remain orthogonal even if their amplitudes and phases are changed. And so what this means is that we can create K orthogonal sinusoids, which we refer to as subcarriers. Each sinusoid gets a unique amplitude and phase shift according to QAM modulation, and then those orthogonal sinusoids are all added together and transmitted simultaneously through the channel. And this QAM modulation we represent by multiplying the subcarrier by a complex term, capital X of K, which is contains the amplitude and phase of the QAM modulation. And so OFDM doesn't transmit just one sinusoid, it transmits K orthogonal sinusoids at the same time added together. And that's where the multiplexing comes from. That's why we call it a multiplexing scheme and not just a modulation scheme. And so in this next slide, I try to illustrate this this notion of OFDM subcarriers in perhaps a little bit more detail. So in this particular picture, I'm showing a 3 subcarrier system where we have 3 orthogonal subcarriers. The first orthogonal subcarrier, when we look at it in the frequency domain, has a delta function frequency response, and x0 would be the magnitude and phase of the QAM modulation being imposed on this orthogonal, or this discrete time sinusoid. And when we take the inverse discrete Fourier transform, we get, obviously a sinusoid with some frequency of oscillation. Our second subcarrier x1 has a different discrete frequency, and x1 again would be a different magnitude and phase for our QAM modulation. We take the inverse discrete Fourier transform, and then we get a waveform that looks like this. Again, a sinusoid with a different oscillation frequency. Then, our final orthogonal subcarrier x of k minus 1 is the QAM modulation magnitude and phase for this sinusoid. We take the inverse discrete Fourier transform of this. In this particular case, it has a 0 oscillation frequency. And then we take all of these orthogonal sinusoids and we add them together. And then our resulting transmitted signal is little x of n. Now, don't forget, we still need to add the cyclic prefix on. So if L is the length of our cyclic prefix, then the length of our transmitted signal x of n goes actually from 0 to L plus k minus 1. So we have L plus k samples. And these L plus k samples are what are known as an OFDM symbol. Next logical question is, how do we generate these orthogonal subcarriers? Well, if, to express the OFDM operation mathematically, we have, again, a summation of orthogonal subcarriers. So here we have a summation of our k orthogonal sinusoids. This is the sinusoid term. This is the orthogonal frequencies, and x are the QAM modulation symbols. And this 1 over root k is just a normalization factor to make sure each sample has unit energy. Now, if this equation looks familiar, it should, because it's just the inverse discrete Fourier transform operation. So this whole equation is just the inverse DFT. Now, OFDM is actually a very old idea. People have been thinking about it for many decades. And when it was originally proposed, people proposed that the orthogonal sinusoids could be generated using analog oscillators. And, while technically possible, this was quite clumsy and resulted in a lot of hardware, and it wasn't perfect. And so it remained kind of an academic sort of idea, but not a practical one. Now, once people realized that if we're working in the discrete domain, that the summation of the OFDM carriers was just the inverse DFT operation, that made it much more efficient, because the DFT can be implemented using the fast Fourier transform operation. And so can be done extremely efficiently, as is well known. And so the IDFT can just be implemented using an inverse FFT, which is extremely efficient and really is the reason why OFDM has become a practical technique. So performing an inverse FFT operation is much more computationally efficient than implementing a big equalizer to deal with the dispersion, and that's why OFDM has an advantage. So in the transmitter, we can generate our sort of transmitted OFDM symbol by adding a bunch of orthogonal sinusoids together using the inverse FFT operation. But what about the receiver? Well, We know from our study of modulation schemes that orthogonal basis functions can be separated by a bank of parallel matched filters. And if we have a matched filter matched to a particular basis function fk, when we look at our convolution operation, as we've studied in the matched filter section, the convolution of the matched filter basically becomes equivalent to a correlation operation where you just multiply the received signal by the basis function and then integrate. Let's let R of n represent the received OFDM symbol after the cyclic prefix has been discarded, right? So we have k samples, not L plus k anymore. Using this, the discrete time version of this correlation equation, we just take the received signal samples, multiply it by the orthogonal sinusoid that we're interested in extracting, right? Think of this as our basis function. And then this summation is just the substitute for the integration in the discrete time domain. So again, if this equation looks familiar, it should, because this is just the discrete Fourier transform equation. And so what happens then is that in the receiver, rather than having a bunch of parallel matched filters, we can just basically take the FFT of our received signal, and the result of our FFT is basically going to give us all of our extracted QAM symbols, just like if we were working with a parallel bank of matched filters. And so the transmitter can be efficiently implemented using the inverse FFT operation. The receiver can be efficiently implemented using the FFT operation. And this is really the beauty of OFDM. So now we're ready to look at a complete OFDM system. And so here I've shown both the transmitter and the receiver communicating through an analog channel. At the input to our transmitter, we have bits. The bits travel through a demultiplexer and go into a block that maps the bits from just ones and zeros to a complex QAM signal vector that contains the magnitude and phase of the QAM symbol that we're trying to transmit. Each one of these blocks generates the QAM symbol for a different orthogonal subcarrier. All of these QAM symbols then go to the inverse DFT operation, or the inverse FFT, and that inverse DFT basically takes all those QAM symbols and in one step generates all of the orthogonal subcarriers, adds them all together. We're then dealing with complex symbols or complex samples. We append our cyclic prefix, and then our complex symbols go into a QAM modulator that converts the real and imaginary signals to an actual transmitted analog signal. We go through our channel. We then have a QAM demodulator that converts back into complex symbols. We discard the cyclic prefix, or basically just select k samples, go through our FFT. At the output of our FFT, we have the QAM symbol for each OFDM orthogonal subcarrier. That passes through a series of parallel detector blocks to convert back into bits, and the bits are then multiplexed together and transmit to, or continue on to the higher layer of the protocol stack. Now, it turns out that while when you look at the OFDM system diagram, it seems to be kind of a complex system. The actual analysis of the OFDM system is relatively straightforward. So let's consider our received samples R, which are equal to the transmitted OFDM symbol X, which contains all of the orthogonal sinusoids, convolved with our dispersive channel, And then we also have our additive noise, which in this case I represent using W. Now, what we do with our received signal samples R is we pass them through the FFT operation. Convolution after an FFT is just multiplication. And so after the FFT, we have basically our QAM symbols, which are equivalent to the frequency response of our OFDM symbol, multiplied by the frequency response of our dispersive channel. The noise corrupting each QAM sample is Wn after going through the parallel match filter bank that's implemented using the FFT operation. Now, it seems like the same noise would be corrupting all of our QAM symbols, but remember that the correlation equations are correlating on orthogonal sinusoids. And so basically what we're doing is we're taking the projection of the additive noise onto a series of orthogonal signal dimensions, which means that the noise that we get then corrupting each of our OFDM carriers is independent or basically manifests as a series of independent random variables. And so if we think of our OFDM system then in the frequency domain, our received signal in the frequency domain is equal to our QAM symbols carried by our orthogonal OFDM subcarriers multiplied by the frequency response of the dispersive channel, the discrete time frequency response of our dispersive channel, plus a vector of noise where each element in the noise vector is independent of the other ones thanks to these orthogonal projections.